is. She did her PhD at Wisconsin with Ben Liblet, and then was a postdoc at UC Berkeley with Kosha Sen. Am I getting all that right?
Yeah.
and is now at UC Davis. She's done a lot of stuff in the space of software engineering, but also in the space of things like floating point accuracy. And actually, I don't know what you're working on these days, so I'm really looking forward to hearing about it.
Yes. Thank you. Okay. So should I use the microphone? Sure.
Prefer to walk around.
Thank you. Thank you for the introduction. I am very excited to be here today. And today I will be talking about some recent work we have done on applied machine learning for software engineering and programming languages, which is Func2vec, a path-based function embedding. And this is joint work with my UC Davis colleague Aditya Thakur and our PhD student Daniel De Vries. Okay. Oh, I have to. Okay, so first I wanted to spend a few minutes talking about, how I got to where I am right now, since this is a mentoring workshop, and there are very few times when I'm able to do that. So I wanted to start by talking about my hometown in Mexico, which I almost never get a chance to talk about. So I was born and raised in Mexico, in a city called Saltillo, and the state is Coahuila in the northeast of Mexico. So Saltillo was founded in the 1500s, and it is known, so for a long time it was known, I don't know if it's still, as the Athens of Mexico, and that was because it was the hometown for many artists, musicians, writers, a very cultural city, music everywhere, and I will explain how I got into music in a few slides. But so it was the Athens of Mexico. Most recently, it has been known as the Detroit of Mexico because of the automotive industry. So yes. And some of the main attractions are museums. So we have very large museums on birds, for example. I was just reading last night that we have over 3,000 species of birds in that museum. And also the area is very well known for finding dinosaur fossils. So just a couple of fun facts about it. So a little bit about my academic background. So I have an interesting background. So I actually attended 2 different universities in Mexico, one to study computer engineering and the other one to study piano performance. So being in Saltillo was a unique opportunity because I was able to study music since I was a child. I actually got into the bachelor's in piano performance when I was 11 years old, and the program was 8 years long, so you were supposed to be there for 8 years. So I got to do middle school, high school at the same time as the piano. And then when I finished high school, I always felt that I wanted to do something else. I never saw myself as a musician. And my dad is an electrical engineer, so back in my head, I knew I wanted to do something in engineering. I didn't know what. So this was mid-90s, a long time ago. So I didn't even own a computer. I didn't know anything about computers. I just got into computer engineering by chance. So I had never programmed. And that was because my dad told me one day, I think computer engineering would be good for you. And I was like, okay, sounds interesting. And that's how I got to it. So not a lot of background there. But then after the bachelor's, one thing that I felt was a challenge for me was that in order to get a job in computer engineering in Mexico, I needed to speak English, and I didn't speak a word of English. So I thought that a good challenge would be to do a master's in the US to force myself to learn English, and that's what I did. So somehow I ended up in Milwaukee, so the only school I applied to, and I got lucky enough to get admitted. And those times were difficult because I would not lie, so I would take my dictionary with me to the exams because I didn't understand anything. I got to TA, and I feel bad for the students I TA for. I don't know how I went by, but yeah. So I did my master's in computer science there. It was a great opportunity. So that's where I got interested in programming languages. So Professor John Boylan is still there. He teaches tons of classes, program analysis, compilers. I took like 7, 8 courses in grad school in programming languages related. So I got in love with it. Then in Milwaukee, everyone talks about Madison. So I ended up going to Madison for my PhD. I spent 6 years there working with Ben Lieblitz, so I had a great time there. Then I guess I had enough of the snow, and I moved to California for 2 years to do my postdoc with Kaushik Sen, Jim Demel, Costin Yanku, and also William Kahan. And then after that, I was lucky enough to be able to stay in California in the area, and I joined UC Davis as an assistant professor in November 2014, so 4.5 years ago. So anyway, long story, so that's where I am right now. So even though I don't play the piano as much anymore, I used to spend my summers playing 10 to 12 hours a day piano, but not anymore. So, but here I still found some pictures so that you believe me. So last quarter it was interesting because I was teaching an undergrad class and some of the students came and said, "Oh, on your website I saw you play piano. I couldn't find you on YouTube." Well, when I was playing, 20 years ago there was no YouTube, so I don't have any videos up, unfortunately. Some pictures from Wisconsin, so I know that there are some people from Madison. So, yeah, very cold, beautiful, but cold. So here is like a nice statue of the mascot, and in the background is basically the Lake Mendota, completely frozen. So it was very, very cold. But yeah, very cool. Now, just a couple of facts before I go into research about UC Davis. So UC Davis is one of the 10 campuses in the University of California. Is the third largest in enrollment after UCLA and Berkeley, and we are the largest in terms of land. And we are in the north of California, close to Sacramento. And one thing for which UC Davis is known is bicycles. So everyone bikes except me. So I'm the only one who doesn't bike. So I just don't know how to bike, unfortunately, but I will learn this summer. And so you can see that even the logo for the city is a high-wheel bicycle. So everyone bikes. A very green city, in terms of sustainability. And we are known for agriculture and the vet school. And just last year, I learned that there is a very popular class that teaches you how to drive a tractor, so I didn't even know that. And this is one of my PhD students who enrolled last year, and he was very proud to send me his pictures. So yeah, so just some facts about it. Anyway, so moving on to research. So I have worked on a few things so far. I just want to tell you a little bit about them, and then we will dive into one of the most recent projects. So one thing that I started doing in grad school was bug finding, right? So I'm really interested in bug finding, really interested in system software, so Linux kernel and drivers, file systems. And for that, I apply static analysis. So I have been working on it throughout the years. So it's something I'm really passionate about. Another thing that I have worked on the past 6 years or so is dynamic analysis for program optimization. So this is for numerical software, so software that uses floating point. So the analyses are meant to help you decide whether you should use float, double, long double, and what is the impact in precision. So lately, or in the last 3 years, I have also been interested in benchmarks. So one thing that we have been working on is building an infrastructure called Bugswarm that automatically creates a large-scale data set of failures and fixes, fully reproducible. It goes from mining to packaging these bugs and fixes in Docker containers. And the hope, so we have over to 3,000 right now for Java and Python, and the hope is that this will open opportunities for our community to evaluate our analysis tools and our testing tools at large scale by removing all the overhead that it takes to actually get real bugs to be reproduced. So that's the hope for Boxhorn. And finally, as many of you in the room, so you may be interested in machine learning. So we have been also looking at machine learning for programming languages and software engineering, and that's what the rest of the talk will be about. So now, some of the motivation for today's work was bug finding, so not surprising. So as I said before, we are interested in system software, so C code basically. And in C code, you don't have nice exceptions, right? Like in Java and C#, where you can throw exceptions and catch them. So basically, all this code uses the return code idiom. You define error codes. You are responsible for propagating them, for handling them, and so on. So one project we were working on was we were interested in understanding how the Linux kernel recovers from errors, right? So what are the recovery actions that need to be taken in order to recover from runtime errors? So we were looking into error handling specifications, and here I have a very simple example. So an error handling specification just tells you what functions you should call when an error occurs, right? So in this particular specification, you see that what it says is that if PCI-enabled device and ksalloc are called successfully and an error occurs, then you should be calling this function SND via 82xx3. So that's all this very simple specification does. Now, so we were successfully finding specifications. So here is another example of a specification. But one problem that these mining techniques face is that all of them find these specifications based on support. So support is how many times you observed a given pattern in the code. And because we are looking at error handling specifications, this is a big problem because error handling is not as common as normal execution code. So you find these specifications, but they have very little support, right? So you find it 2-3 times, and then you cannot tell whether they are a true specification or a false positive. So this is a very big problem when mining these kinds of specifications. So that gave us, the inspiration to look more. So if you look at these two specifications, you can see that they are almost identical, except for the right-hand side, right? Like the functions in blue. So what we did was to look more into these functions to see what made these specifications different, right? Because if you just look at them, they don't match. So that brought us to the work I will present today. So in particular, we were looking at these two functions, and it turned out that one specification was coming from one driver, the other specification from the other driver, and these functions in blue were implementations from each of those. So from the name here, and it's not always the case, this is just a nice example, we can see that even though these functions are different, they play the same role or purpose, which is critical for the specifications we're finding. At the same time, you can see that because these belong to different drivers, they may be syntactically and semantically dissimilar. So if you just do clone detection, you will not find them. But still, they have the same role or purpose. So what we did was to refer to these functions as function synonyms. And now if we go back to our motivation, this is an application of function synonyms. Because now, if I come across these two specifications, and I find that the difference, the functions in blue are function synonyms, then I could merge these specifications and increase the support. And this will really help when determining whether these specifications are true specifications in our results. Okay? So that was the application. So that's how we came to the realization of function synonyms. So now what I will do is tell you how we find these function synonyms using machine learning. So one observation here was what is known as the distributional hypothesis for natural language. So this says that words that appear in similar contexts tend to have similar meanings. And here is a very simple example. So we have two sentences. The dog has a big bone, the dog has a large bone. And here what we find is that big and large have similar meanings because we find that these words are used in similar contexts. So this is what the distributional hypothesis for natural language says. Now, how does this look for software? So that's what we're trying to define. So if we want the distributional hypothesis for software, what it says is that functions that appear in similar contexts along program paths tend to be function synonyms. So that's our premise. So here the analogous would be program paths. So imagine assume that you have these two paths. This is just list of instructions in the program abstracted. So if you find two functions that are called in similar contexts along program paths, then we could refer to these functions as function synonyms. So this is the idea. Now, what we did was to develop a tool or a technique called Func2vec. So what Func2vec does is that it computes an embedding that maps each function to a vector in a continuous vector space such that vectors for function synonyms are closer to each other. So we're trying to mimic what the natural language processing community has done in the past for finding similar words in text. So the output of Func2vec, for example, for sound drivers, is here. So this is just a two-dimensional projection using TSNE. But you can see already clusters of functions based on functionality. So for example, you can see here the upside-down red triangles that correspond to the free functions in the drivers. And there you can find the two functions from our example. And similarly, you can find a nice cluster of functions for open, functions for suspend, function for remove, and so on. So what we want to do is to create this embedding so that we can use it to identify function synonyms. So luckily, there has been recent advances that have provided techniques to produce embeddings for a corpus of text in a very scalable way. And one of these is Word2vec. So Word2vec takes as input sentences, and it creates a model, right? So a distributed representation of the words in the vocabulary. So what we want to do is to find a way to encode the program so that we can still use Word2vec as it is. So it's still a black box for us. So it would be interesting to get, into this box and understand better how it works and how we can make it better. But for now, we still use it as a black box. But now here the main challenge is how to encode the program so that we can fit these sentences to Word2vec so that we can get a model that corresponds to the Func2vec model. And so I will just walk you through a very tiny example to give you an idea of how the technique works. So here is a tiny example. So this function doesn't do anything very interesting. So basically, it calls an init function. If it is successful, it calls an init and returns 0. If it's unsuccessful, it just returns an error code. But we will be using this running example just to show you how the algorithm works. So the very first thing we do is that we construct the interprocedural control flow of the graph. And so here is a simplified version that corresponds to that piece of code. And what we want is to linearize the program so that we can produce sentences that we can give to Word2vec. And one naive approach is to create these sentences using instructions, the instructions that appear in every valid interprocedural path in your program. Now, the problem with that is that now these sentences are going to correspond to a very large vocabulary that is not going to give us anything really useful. So one solution to this, as it is a solution for many problems in our domain, is abstraction, right? So why don't we abstract these instructions? So that's what we do. So by abstraction, I mean that every instruction is associated with a label. So for example, if we find a statement that corresponds to a function call, we simply replace that with a label that includes the name of the function we're calling. If we have a conditional, we abstract it to be just the operator, in that conditional. If we have a statement that involves an error code, which is important for the application we are looking at, we just keep the name of the error code and so on. So that's the level of abstraction that we do. So now, how about we linearize the program by listing all the labels along every valid interprocedural path in the program? However, the next problem is path explosion, right? So we might have an infinite number of paths. So how do we solve that? So to tackle that, what we did was to propose an algorithm that randomly walks the interprocedural control flow graph of the program. So what this really does is that it's going to bound the number of paths that we are going to create for each label and also the length. So basically what the algorithm does is that you select an edge with a label. So let's say I select that node, and then you start walking the interprocedural control flow graph. So every time you cross an edge, you speed that out. That will be a sentence. And in this case, we're done. So let's say that we start there. So this would be basically the sentence. When you have more than one, path or option to follow, you pick one at random, and so on. And then you are going to determine how many paths per label you want, and also what is the maximum length. And this will solve the problem of having an infinite number of paths. So finally, one of the problems is that this algorithm, as I describe it, doesn't leverage the hierarchical structure of the program, right? So let me give you an example to show what that means. So here is the same control flow graph that I had, except that I added this kmalloc and generic init that are called from the driver a init. And let's say that I have this other portion of the interprocedural control flow graph, and these are the functions in inits, right? So driver b on init and driver a on init. So I want to identify them based on the context in which these functions are called. And you can see here that these functions indeed are called in similar context. So you see that b on init is called, after calling kmalloc and generic init, and the same for driver a on init. But if we just apply the random walker as I describe it, we're not going to be able to find them because driver a on init is going to be associated with the context where driver a init is called, and not with what happens inside. So in other words, we have to go, whenever there is a call, we have to decide, how many steps to go into the call. So one solution to that is that whenever we find a function call, we can either step into the function, so we can randomly decide if we're going to step into the function. In this case, we're going to record kmalloc, generic init, and that's it, and then we continue. Or we could also decide just to step over the function call, in which case we would associate the function with the function itself, the driver a init. So it turns out that this helps us to make the association so a function can be associated with what happens before that, and also with the context of the value of the function, basically. So that's basically, in a nutshell, what the algorithm does. And so in summary, so we build the interprocedural control flow graph, we abstract instructions, and then we apply this random walker. Yes. And we feed them into Func2vec, and we get this model. So I'm not going to talk a lot about the evaluation. So we have an FSC paper on this. We evaluate this on several metrics. So in particular, we look at a runnable Linux kernel with about 2 million lines of code, and there are like that many distinct labels, and we do a grid search to find how many walks and how many, what the length of the path that works better. So let me just show you really quick. Let me just. So I just wanted to show you that, so this is part of the model that we have here in TensorBoard. So it's really cool because you can move it around, and these are basically functions, and you can see the groupings. You can also search for a specific function, like via 82 XX free, and then basically it will tell you everything that is close to it. So all the code is available in GitHub and the data. So if you feel like playing with that, you can. So let me. Okay. Okay. And just to wrap up, so I'm going to skip that. So going back to the error handling specifications, these function embeddings were really, really helpful. So these are the examples I showed at the very beginning, for which the support was very, very low, 6 and 4. So it turns out that that specification was also found across many other device drivers. And at the end, we could merge these specifications and bring support from 2 and 3 to over 100, which is really, really good. What we use this, I'm not explaining today how we get the specifications, but one thing that we did with them was to do bug finding. So basically finding violations to these specifications. And one way to find violations is to find instances in which you see basically the left-hand side, the context, but not the right-hand side, what you need to do in order to recover from the error. And we found a bunch of these bugs to Linux, the Linux community, and some of them have been fixed, and they are now part of the Red Hat distribution. So just to summarize, so today I talked a little bit about our recent work on function synonyms and how we use Func2vec to find them, a fun application of specification mining. And here is the link to all the data and the code. And yeah, so I'm ready to take any questions. Thank you. Yeah, so that's a metric that, oh yeah, so the question was whether we have used cosine similarity to find these functions. So that's a metric that we use from the model to identify what's close, what functions are close to each other. So we did a lot of studies before getting into this, into like comparing the names of functions, but that wasn't as effective. So I couldn't talk about the evaluation today, but basically we have a gold standard of thousands of functions that we selected in collaboration with a Linux developer. And we made sure that that standard includes function synonyms that both follow a naming convention, such as the free functions. And also we have thousands of pairs in which a naming convention is followed, but those are not function synonyms. So we have like all the cases. Yes, so the question is how we could apply this technique in a scenario for a language, perhaps Java, right, with inheritance. So that's a very interesting question. So I think that one of the main challenges in there will be to have a precise interprocedural control flow graph, because it might not be straightforward to resolve statically what functions are going to be called. But other than that, I think that we might be able to include more domain knowledge if we know that some functions, because of inheritance, might be similar. But the algorithm itself, the walker, I think that it should work. It should work irrespective of the language if you have the control flow graph. Yeah.
All right, let's thank Cindy again.
Thank you.